Okay, now without further ado, let's move to the first session, large-scale cryptography. We will have two talks from people working at Google and Amazon, respectively. And like, I don't need to tell you that whatever these companies deploy affects the life and the security of millions of people. So that's why we're interested in this kind of cryptography. And this leads me to introduce our first speaker, Ghous. So Ghous is a researcher and software engineer in the private computing team at Google in New York. His background includes a PhD in cryptography, focused on encrypted search at Brown University. And Ghous will be telling us about the deployment of anonymous tokens with public metadata within Google. Sadly, Ghous was not able to travel here, so it will be our only remote talk.
Take it away, please.
All right. Okay. Hi, everyone. I can't see you, but I'm assuming I'm talking to people right now. So my name is Ghous, and today I'll be presenting our work on RSA blind signatures with public metadata. This is a joint work with Kevin Yeo and Moti Young, part of the private computing team at Google NYC. So this talk is roughly divided into 6 sections. I'll motivate the problem, go over some required high-level background, give some overview of the main protocol, very briefly discuss the security of the protocol, and go over implementation benchmarks, and finish off with some updates on the latest status of the protocol in terms of production deployment of our work. So let's start. Blind signatures, or anonymous tokens, if you will, are a core component of for improving privacy of several real-world applications, including authorization protocols, VPN spam detection, private ad measurement, Tor denial of service defenses, and so on. In these examples, they're mainly used as a way for one party to gain another party's trust. Basically, by presenting a blind signature, the first party lets the second party know that it is allowed to do something depending on the application, while the first party maintains their anonymity. And in certain applications, it's natural to associate signatures with specific public metadata, basically to ensure that trust is only propagated in respect to a certain set of users or scenarios. For example, real-world use cases for public metadata may include when blind signatures need to have a short expiration time, or when they need to be valid with respect to certain locations, and so on. One can imagine having different signing keys for different metadata, but this may require to fix public metadata choices ahead of time, as well as this is a deal breaker in major applications because of key management scalability concerns. Because when you have a large number of keys and along with key rotations in a real production system, it's a big headache, and it could lead to potential mistakes such as missing keys and bringing services down. Finally, there are work streams already in place to build real-world architectures that rely on partially blind signatures in the IRTF Privacy Pass Working Group. Schemes in this paper can be so scheme in our work is basically one variant that fulfills a requirement of Privacy Pass. So it was adopted by the Privacy Pass draft. The Privacy Pass draft basically mentions 2 flavors of schemes with public metadata. One is the privately verifiable scheme, where only the party holding the signing key can verify. And one is the publicly verifiable variant, where anybody with a public key can verify a signature. And our work falls in that that's side of the draft. But why did we go for RSA blind signatures? So for one reason, it's RSA blind signatures are a simple one round scheme that have a stateless server issuance, and it has widely supported cryptography available in major platforms. So it's natural to think of like a variant that supports public metadata as well. And before we go to discuss that variant, we'll refresh what blind signatures, what blind RSA signatures are. So there are typically 3 different roles in a blind signature scheme. One is the user or client that is requesting the signature. The other is the server or the signer that basically issues the signature. Who holds the public key and who publishes the public key and holds the secret key. And then, for example, let's say the client has a message, virtual presentation sad face, that it wants to send to the server without revealing it to the server. The server, on the other hand, like I said, holds a public key and gives it to the client. Under the hood, the public key is basically for RSA blind signatures, basically the public modulus n and the public exponent e, and the secret key is the private exponent d, where e is basically the modular multiplicative inverse of d, modulo the Euler-Stoichern function, and that's all we need to know for the purposes of this talk about what the Euler-Stoichern function is. Now, a client on the has so the client with the public key in a message wants to essentially first blind that message before sending it to server. So in the scheme, we first hash the message using a message hash function, and then give it to the blind protocol, which outputs a blinded message and an inverse that we store for later. We send the blinded message to the server. The server then uses the secret key, signs the blinded message, and sends a blinded signature back to the client. Now, under the hood, again, it's basically the blinding message is basically the hash of the message multiplied by some blinding factor r raised to the public exponent. And the inverse is basically the inverse of the blinding factor, r inverse. And when the server signs it, it basically raises this whole value to the private exponent d, which essentially cancels the effect of E on R, and you can probably already guess where it's going next. The server sends the blind signature back to the client. Now, for the final part, the client finalizes this blinded signature to produce the final signature, which is basically multiplying the server output with R inverse to cancel out R, and we are left with the signature. Now, the signature is publicly verifiable, so anyone with the public key can verify it. And here you basically just need to raise the power with the public exponent and see if it's equal to the hash of the inputted message. Now, let's move on to RSA blind signatures with public metadata, or basically partially blind RSA signatures, if you will. The main difference between blind and partially blind signatures is that you have public metadata D in all the protocols known to all parties. So in blind sign, finalize, and verify, the same public metadata is accessible. The scheme we will present is basically a modification of a scheme by Abe and Fujisaki. Our main contribution, however, is proving the security of this adjusted scheme, as the previous work dealt with heuristic security and also had some unnecessary computations. So as a first change to the blind signature scheme, we made sure to augment the public metadata with the input message before passing it to the hash function h of m. Sorry, this should be h of m here. Now, so for in the diagram, we're basically passing concatenating the public metadata of the message file before blinding it, and sending it to the server, and the server also uses the public metadata during the blind sign protocol. Now the server needs to do something with the public metadata, otherwise the client can lie about the augmented public metadata during verification. So what happens is essentially under the hood, instead of the public exponent e, we derive the public exponent using the public metadata. Secondly, for derivation, we basically use a HMAC-based key derivation function. This is just for ease of implementation. And sorry, one second. I should mention something else here. No, that's it. Okay. So instead of like R to the E, now you're raising R to the H of D. And instead of the private exponent D, we have H to the D inverse, which the server computes. So the question becomes, does H of D always exist? And for that to be always true, for it to be always exist, what H of D inverse needs what H of D needs to be is to be co-prime with the Euler-Stoichern function that I mentioned earlier, where n is the RSA modulus. And what we do a simple trick in order for this to happen. We, instead of using RSA modulus, we use a strong RSA modulus, which is basically product of two safe primes. You don't need to know what safe primes are, but what we do is essentially, what essentially it does, it gives the value of the Euler-Stoichern function a structure such that if we restrict the length of h of d to be less than those safe primes, and we make sure h of d is always odd, then we get coprimality with the Euler-Stoichhian function. And in that way, we guarantee that the scheme will always have a h of d inverse for any public metadata d. Now, finalize is basically the same as before. R just cancels out on inverse. And for verify, instead of raising to the public exponent e, we raise it to h of t. So we already noted that the prior work did not have formal definitions for security. One of the main contributions in our paper is proving that a modified version of their scheme is secure. So we prove the security for one more RSA assumption with multiple exponents that we introduce. Uh, that is the assumption that we prove the security of our protocol from. And before looking into it, let's see what the standard one more RSA assumption is. So in that assumption, adversary is given access to an RSA oracle, which takes in input x and outputs y, where y to the public exponent e equals x modulo n. And we get a challenge oracle O of x. The adversary wins if it finds the eth root of L+1 challenges from the challenge oracle, with at most L queries to the RSA oracle. Now, what we do is we extend this assumption, the assumption in the previous slide, to a new assumption that we call multiple exponent, one more restricted multiple exponent RSA assumption, in the style of one more style techniques of Billare and other people. And to our knowledge, this is the first exploration of one more RSA assumption, RSA inversion assumptions with multiple exponents. So the adversary is additionally given an access to an exponent, the oracle exponent, and the RSA oracle takes additional input. It takes basically an exponent as an input, and now you're outputting y. That is that exponent root of x. So the adversary wins here if it finds the e prime root of x+1 challenges from the challenge oracle for some exponent e prime from the exponent oracle. Hence, because we are with at most x queries to the RSA oracle for that particular exponent. And now we call this assumption the restricted assumption because we are restricting the oracle, restricting the exponents used to the exponent oracle, to only exponents outputted by the exponent oracle. And now, furthermore, we furthermore modify this to an algebraically restricted exponent assumption, where we show that our scheme basically reduces to this algebraically restricted exponent assumption. And here, the difference is only that we make sure that the exponent oracle output exponents that preserve a certain algebraic property with respect to each other. And this sort of gives you a clue to the fact that it might exist an attack on the scheme if the exponents do not preserve that algebraic property. In our paper, however, we show that the public metadata universe size is selected appropriately and output size of the public exponent derivation hash function is high. The probability of success of such an attack is very low and its running time is very high. Now, in other security considerations, we went on to prove the one more unforgeability of our scheme using modified definitions, modified for the case of public metadata. One more unforgeability in the setting of blind signatures is basically that no party is able to generate signatures that will correctly verify unless they have access to the private signing key. We also prove unlinkability for under a modified definition of public metadata, where this property essentially captures the fact that a signer should not be able to link blind signing requests with final signatures. During implementation, we made sure that we make sure that make sure about domain separation. For example, in different RSA moduli will ensure different derived public keys for same public metadata, as well as hash function for input message augmentation, as well as public key derivation and domain separated during implementation. We also underwent a third-party audit of our cryptography by the NCC group that also verified our paper's claims in a public report. So this is a tough one. So public metadata adds an important tool in our toolkit to stop bad actors or reduce damage they usually do. But one can imagine at some point, if we keep expanding how much we put in the public metadata, we can start identifying users, right? There needs to be a delicate balance here, such that the the property that a blind signatures give, i.e., blindness, stays. Um, so clearly, the metadata should not contain overtly sensitive information. You should never put like direct user identifiers in them. That's bad. it should also be fully inspectable by the client because we need some sort of transparency or accountability. So we should announce expected fields with their pre-established possible values, and these values should be low entropy values. So a lot of people should end up with the same values. In our use cases, uh, um, that those that came up, we, for example, in one of our use cases, we restricted public metadata only to contain course locations like country level information. And in other cases, we made sure that the online population of at least 1 million per public metadata is present before, uh, uh, otherwise that public metadata is not good, um, and so on. Okay, so now let's talk a little bit about numbers. We show that a protocol incurs only slight overhead over the standard RSA blind signatures. This is done for the RSA modulus size of 2048 bits. Um, partially blind signatures take a little more time in all of these protocols than the standard blind RSA signatures because the exponent that we derive using public metadata is pretty large compared to what we usually use in practice for the standard version. There are three available implementations right now. One is in C++ by us. The other one is from Chris Wood. That's in Go. And there is also a TypeScript implementation by CAW of the same protocol. Yeah, and they all follow the same. A standard draft that is already available on IRTF website. And finally, let's talk about the current status of this work and the deployment in production. So at Google, we are using this in Chrome IP protection authentication. Here, basically, um, your user requests are routed to different CDNs, and they're stripped away of their IP addresses. So when they end up at Google, we don't get information about where this request is coming from. And during these hops between CDNs, in order for one hop to authenticate to another hop, these tokens, these partially blind RSA signatures are being used. They're also being used in Pixel VPN authentication. Again, here also, they're being used for things like, um, so for example, we want that if somebody is allowed to use the VPN in a certain country, only a token tied to that country can authenticate the user in an anonymous way, so that they're basically trying to use a VPN. We shouldn't know what they're doing or what they're and who they are before they use it. And then uh, automatic key rotation of keys are done on a bi-monthly basis without any service interruption. Improvement in end-to-end latencies was also achieved using different caching mechanisms because sometimes the public metadata derivation and their inverses are used across different public metadata, right? So by caching those in a timely manner, we avoid extra computation cycles. So this paper is set to appear on POPEX 2025. The ePrint is available online if anybody who's interested in it. A standards draft for this protocol was adopted by the CFRG, where CFRG is a crypto group inside the IETF. Now, finally, I present the anonymous telemetry for real-world deployment. This showcases our scheme scalability. So these are basically a mix of sign and verification queries between March 10 to March 24. We averaged around like 9.7 queries per second. Um, uh, um, so the median and P90 latencies were a couple of milliseconds for sign and for sign queries. For verification queries, the the signature redemption latencies were around 100 milliseconds to 250 milliseconds. The reason for this high latency comes due to the fact that we also don't want double spending of a blind token. So once a token is spent, in order to prevent double spending, we have to do some database reads and writes to check if we can still allow that token to go through. And that pretty much wraps up my talk. Thank you for listening to it.
Right? Yes. First of all, thank you guys for giving the talk. It's not saying thank you for giving the talk in the middle of the night for you.
No worries.
Is there any question from the audience? And otherwise, maybe I will.
I posted. There's one in the queue, right?
There's one
virtual
Yeah, I
one.
think that
Okay.
hashing to an exponent and inverting looks like other schemes, e.g. Cox QR-based ID schemes. Are there other schemes you know of that use similar construction? Do you think your assumption could be generalized to include these?
Surprisingly, no, I wasn't familiar with these other schemes. The assumptions I would think could be generalized because I feel like some of the we'd explored it for specifically for RSA in particular. But I can see like having a general security definition that could talk about that could capture this basically this exponents and the inversions. Yeah.
We have a second question also on that.
What are the privacy guarantees?
Oh yes, what are the, like I also wanted to talk about this, so it seems like some thought went into like trying to keep this private, but for instance you mentioned that like some metadata attributes are like guaranteed to have a population size of 1 million.
Yeah.
Can still be several bits of, like if it's 1 million out of 1 billion, it's already several bits of identifying information, and then combining various attributes together, you can probably still identify. So like maybe what are the privacy considerations and like the processes to get?
Yeah, so what essentially they tried to do here is we tried to keep the bulk metadata as coarse as possible, like not like the geolocation hints are usually like country level hints, and even the time expiries are essentially coarsened to the nearest like 15-minute, 20-minute window, such that between those 15-20 minutes there are enough users that we're not able to exactly learn or like exactly end up identifying people. So it's a bit of a so the privacy guarantees on paper are basically that, you know, your blind token is essentially blind with respect to like a public metadata, right? Under a fixed public metadata, your token is as blind as the next one with the same public metadata. But obviously in practice, this devolves into just making sure that people are using it the right way and not being malicious with it.
All right.
I think we should
Yeah.
move on to the
Well,
next session.
thank
Let's
you.
Thank you.